Good evening. My name is Ranga Gopalakrishnan. I'm an associate professor in this department. I'm the instructor for this course this semester, Engineering Analysis 1. I see there is about 4 students enrolled for the 7,000 version and about 13 enrolled for the 8,000 version. So, if you are a master student, you are usually taking the 7,73414, and if you are a PhD student, you're taking the 83414. Please come in. So I posted this syllabus. I think I made a few revisions and finalized it on Friday. I hope you had a chance to download it and see. If I'm going to go through this in the first few minutes and then we'll step into the course topics. Okay. And along the way, feel free to ask questions if something is not clear. Um, I want to spend about 20 minutes trying to explain the course structure to you, and I want you to be very clear of the expectations from the beginning so that you would do well. Okay, so feel free to interrupt me and ask questions. Um, I don't set aside office hours specifically. Usually, I work with the student to find appointments to meet and discuss because not many students come to these office hours. It's much more efficient if I meet with those that need help. So feel free to shoot me an email. Tell me when you would like to meet, what is your issue. Sometimes I might be able to help you through email itself, or sometimes we can meet and talk. Okay. If suppose I'm not on campus, at least I'll make effort to meet you through Teams, and one way or the other, I'll give you time to ask your questions. Okay. Course description. As the title suggests, this course is focused on analysis to help you learn mathematical techniques that will help you do engineering analysis. So there will be a lot of techniques that we will learn and apply it for engineering problems. So most of your homework and exam problems will be word problems in which there will be a context, and you will have to apply the techniques you learn in this class for solving those problems. So it won't be like just like solve this equation. It won't be that simple. It will typically involve some physics or engineering situation. Analysis of engineering systems using closed form solutions. What we imply there is no numerical methods. We are not going to discretize an equation and solve it. We are going to learn analytical techniques like either power series techniques, Fourier transforms, Laplace transforms, those kind of mathematical techniques. Okay, no numerical methods. Application of Fourier series and Fourier transforms, Laplace transforms, power series methods, vector calculus, ordinary and partial differential equations. So this is the course description, and within that description, I construct my set of topics and syllabus and how I administer this course. So that's what the rest of the syllabus is. Um, 10th edition of Erwin Kreyszig's book, which is very common. You can easily find it online. You can buy a paper copy, electronic copy, whatever is convenient for you. Course topics or schedule. Um, I will make every effort on my side to stick to the schedule. I have assigned these number of lectures for each topic depending on how much time I think it will take me to discuss them. May take a little more, little less, but I'll worry about it. What you should worry about is the topics given here. And as you will see shortly, there are going to be 3 exams. Each exam is going to cover 2 modules. So there is 6 modules in the course. So that when we finish two modules, immediately follow that to the next exam. That's the structure we are going to follow. And then there are going to be 2 projects in the course. I'll talk about that. So overall, I've come up with a structure in which I evaluate your understanding through 3 exams. Each exam covers 2 modules only those 2 modules. It's not cumulative or comprehensive. And there are not going to be homeworks assigned for grade. I'm going to assign suggestive problems. I encourage you to solve those, which I think will help you learn the material better and face the exam better. So the exam is going to be for 75 minutes covering two topics. You might have 3 or 4 problems or 5 problems, but it will just be on those 2 topics. So Sometimes it's hard to say exactly. I'll give you 3 problems. It might be 3 to 5. Okay, it could be. I've planned those for 3 specific dates. Third week of September, October 28th, and November 25th, right before Thanksgiving. So that is already 60% of the course credit. Okay. No homeworks. The homeworks are assigned, or in the sense they are posted online, but you don't have to prepare solutions and submit them to me. What you need to do is be truthful to yourself, do those problems. If you get stuck somewhere, or if you want to discuss, you can do it with your friends or do it with me. Make sure you understand the material through those exercises. That will prepare you for the exams. Proof of the pudding is in the eating. I will test you at the exam. I won't be coming after you to make you do homework. You're all graduate students. I give you the opportunity to be responsible and the chance to fail if you fail to be responsible. Okay. And then there are 2 other instruments of assessment in the course, 2 projects, one of which is based on module 2. And you may ask, what is module 2? Module 2 is series solutions of ordinary differential equations, your Legendre polynomials, your Bessel functions. So it will be a engineering or a physics problem that you choose and solve using the techniques that you learned in module 2. That is the first project. So it typically involves you selecting a problem, setting up the differential equation that describes the problem, solve it using the methods we learned, present the solution, and all of this you will write as a report. That is project 1. Okay. Project 2 is pretty much the same, except project 2 is based on module 4, which is partial differential equations. So one of them is ODE, other is PDE. Okay. Same procedure, you would select a problem, set it up, identify boundary conditions, solve it, discuss the solution, except project 2 will not be a report, it will be a class presentation. So each of you will get about 10 minutes or so to make a presentation to the entire class, and I will assess you based on your presentation. Okay. So that adds up to 60 plus 40, 100%. Okay. So there are no other submissions, 3 exams, 2 projects. Okay. Questions so far? Yes. Sit down, sit down.
In case of projects, so do you pick the problem?
I would encourage you to do that, especially for those taking the 8,000 level class. I require you to do that. For those taking the 7,000 level class, if you are unable to pick, I'll help you pick or pick one for you. Yeah. I'll share some examples on what students have typically done in the past to give you an idea. We'll do that a little bit maybe towards the end of next lecture. I don't want to get drawn into that right now. After we have seen some real math, I'll then kind of talk about the project content, like show you some examples. Other questions? Okay. Following that is the 100%. You can see that there is no final exam. All your assessments are done within the lecture schedule itself. The last 2 lectures will be class presentation. So there are 17 students as of now registered for the course. If each gets 10 minutes, that's 170 minutes. One lecture is 85 minutes long. So we get 2 lectures. We kind of manage 17 presentations. You will have to be present for the day in which you are presenting as well as you are not presenting. Okay, so that you support your classmates. Okay. So following that, I have the letter grading scheme listed here. This is a pretty aggressive scale. You see here, to get an A, you'll have to score 97% or more, which essentially means you have to ace all the exams and do well in your presentations with some margin for error. If you are going to botch one exam, you can forget 8. If you end up scoring, say, 15% out of 20% in an exam, you're done. You have to move from A to A minus, and that's the highest you could aspire for. I know you're all graduate students. You wish to get straight A's in your transcript and be, impressive. But to be impressive in this grading scale, there is almost no margin for error. I want you to understand at the beginning. Okay, so it's a very sort of risky if you are not working hard. That is, if I give you the responsibility of trying the examples on your own, and you just think nobody is there to ask me for homework, I'll just take it easy, then your grade will not be good. So I hope I'm scaring you enough that you will kind of sit up and take notice. Any questions? You can speak. You're allowed to speak. So, sorry, what was that? So A minus is pretty broad compared to A. There's about like 6% bandwidth for A minus, B plus, B minus. At the graduate level, typically a C is like almost failing. You want to get a grade better than B plus or A minus, which shows that you worked hard for this course. Please don't fall into this category or worse this category. I want you to work hard on this course. I'm trying to make it very clear. It's a tough course, the way I've set it up, but hopefully you will learn enough from this. Okay. Homework, like I said, examples will be solved in class, and the 6 documents that I posted, like essentially I on eCourseware or Canvas, I have posted homework 1, homework 2, etc. with section numbers. These are the sections I intend to go over during lecture. And these are problem sets or problems that I'm suggesting as a minimum, not as a maximum. If you at least do these, you will get an idea of what went on during lecture. If you don't do these and show up for exam will be difficult. That's what you should understand. And you should do much more than these to get your practice in. Okay. And yeah.
Do you base your exams off of homework?
In a general sense, yes, but do not expect these problems to show up directly. Okay. Most of the exam problems will be like a word problem that not only expects you to use a mathematical technique, but also to kind of distill the text and synthesize the equation that need to be solved. And most often it will be like either use method A or method B, both of which are about the same difficulty, but your skill lies in how you can read a word problem and reduce it to the equation, identify boundary conditions, and then actually solve it. So that the course title is not engineering mathematics, it is engineering analysis. So you have to do the analysis. Okay. So I thought some other hand went up. Um, yeah. So no formal homework will be assigned or solutions collected. You are responsible for practicing problems. At the graduate level, what are you looking for in a course? Unlike when you did your undergrad, what is the difference when you come over to this side? What do you guys think? Just few responses from you.
It's research.
You all might be doing research, some of you at least, and in this year, at least in this class, there are more doctoral students than master students this time. Usually it's the other way. Usually it's the master students that are like 15 and doctoral students are 5 or 6 in this department, but the trend has reversed. I assume you're all doing some kind of research. And when you're doing research, you would work with softwares or packages which give you numbers. But knowing the math and having the intuition to at least expect what your software is going to say is a key skill. you can't just rely on your ANSYS or your COMSOL or your OpenFOAM to just tell you a number, and you can't take it at face value. You need to be able to model engineering problems and be able to have expectations for what the answer is so that you can cross check your calculations. Or if you're doing an experiment, you need to have like a simple back of the envelope estimate of what your uh, value is going to be. You need to know some basic mathematics. That's what this course is trying to teach. Okay. So I will not get very prescriptive about which exact problem, which exact type will appear on the exam. I want you to look at the topics and be able to understand, do enough problems to master each topic. Okay, that's the goal. I already talked about the two projects which are worth 40%. It will be setting up a partial or ordinary differential equation to model a engineering or physics problem using the methods developed in module 2 and module 4. If you need help with selecting the problem, I'll be very happy to help. And then there are 3 exams, each worth 20%, no comprehensive exam. This is a typo, it has to be 75 minutes. I just want to give you the maximum time I can. The exams will not be computer based. The exams will be pencil, paper, and calculator. So even though you are good in programming and setting up a code to do the number crunching for you, in the exam, the skill being tested is whether can you do the calculations yourself. Okay, so remember that difference. Any questions?
If the exam is open book, can you?
I have not decided about that yet. We'll figure it out as we go. You all look like a very eager bunch, so maybe closed book. Maybe you'll just knock it out of the park. You don't need no book. Yeah, we'll see. And the rest of the syllabus is university policies on integrity, collaboration, classroom behavior, no plagiarism, no inappropriate collaboration, especially in exams. The projects, the exams are all individual assignments. You don't get to do group projects. Each one of you have to do your own project. Is that clear? Nobody is going to work together and submit the same thing in 2 copies, nothing like that. That will be taken as plagiarism. Okay. You can read the rest of the syllabus, which is essentially university policies that I pasted there. Okay. If there are any other questions, otherwise I can start with the topics. Okay. All right, give me 1 second. So the prerequisite for the course is, broadly speaking, graduate standing, meaning you have done your undergraduate in some discipline related to mechanical engineering, or at least you know something about differential equations and math. I assume that. So I'm not going to explain what is an ODE, or I'm not going to, the spirit of the course is more focused on learning techniques and less about theory like real mathematicians. So that's why we carefully named it engineering analysis without calling it engineering mathematics. Because if a mathematician shows up and asks, oh, what about existence and uniqueness? I have no idea. I'll be like, I want some numbers that I can test in the lab. Hello, not a mathematician. Okay. So that's why we want to keep it more focused on uh, methods, procedures, and less about theory. Okay. If you know more about theory, feel free to share with the class, but I'll tell you, I don't. I'm an engineer. I would like to stay one. Okay. All right. So as far as the first module is concerned, um, it module 1 is ordinary differential equations. It is covered in chapters 1 and 2 of crazy. Okay, chapters 1 and 2. And if you want to know exactly the section numbers I plan to teach, that is given under homework 1 and homework 2. At least as far as chapter 1 is concerned, I'm thinking of discussing section 1.3, 1.4, and 1.5. And chapter 2, I am planning to do 2.1, 2.2, 2.7, and if I end up having more time than I thought, I might add some more to that. If you look at chapters 3 and 4, 3 is nothing but higher order ODEs, and 4 is systems of ODEs. I won't have time to discuss these two, but what you will find out is that 3 and 4 are really an application of 1 and 2. If you know your way around 1 and 2, you would be able to at least be able to make sense of some examples there. So depending on how much time we get, I'll try to squeeze in an example from these into the lecture. Depending on that, I'll tell you what exactly is going to be on the test, in the sense, see, this is definitely going to be on there. This depends on timing. Okay. Okay. So with that, can really start. So so in general, we want to write if we have dy by dx equal to a function of x and y. We call this a ordinary differential equation. And there are, within ordinary differential equations, some have a special form. We call them, you have this, and if you are able to write, you are able to write this equation as g of y times y dash equal to f of x. Since I'm using f here, I'm going to change this to h. Okay. This form is called a variable separable form. What that implies is the left hand side contains only terms that involve y, and the right hand side contains only x. So that it's easy to integrate, and we would be able to write this as g of y dy equal to f of x dx. And if you want to integrate both sides, that would be, you'll have to add an integration constant. So if you actually carry out the integration, you get a solution. Okay. We'll do like a very simple example. Y cube y dash plus x squared equal to 0. You probably, not probably, you will definitely know this. All you have to do is separate the terms, write this as y cube dy plus x cube dx equal to 0, or x squared dx equal to 0. What is y cube dy? That is the differential of y to the fourth over 4 plus differential of x to the third power over 3 equal to 0. And then integrate each term or both sides, however you want to call it. That will be y to the fourth over 4 plus x cube over 3 equal to a constant. This solution, which has what is called as an arbitrary constant, is called the general solution of the ODE. Is the general solution of the ODE. What we sort of implicitly say here is x and y are some kind of spatial variables, so that if you know the value of the function at one point, you could in principle evaluate C and get rid of it. That is, if you are provided, for example, y at x equal to 0, let's say that value is 0. Suppose this is given. You can then say 0 to the 4 over 4 over 4 plus 0 cube over 3 equal to C, which obviously implies C is 0. So then you would say y to the 4th over 4 plus x cube over 3 equal to 0. This without any arbitrary constant is called a particular solution. I know what you're thinking. This is so simple, so easy. Why is he taking 10 minutes to talk about? It's just to introduce the idea of arbitrary constant, general solution, and particular solution, because as we go on, it will get complicated, but these concepts will remain of the idea of a particular solution evaluated using a boundary condition or an initial condition, and the idea of a general solution which contains arbitrary constants. Yes. Did you have a question? No? You are allowed to ask questions. This section 1.3 is essentially to do this variable separation form. The very straightforward concept, not going to discuss it further. We are going to skip to the next section, which is related to integrating factors. Okay, what is integrating factor? So section 1.3 talks about variable separable form. Okay, something in which you can write g of y dy plus f of x dx equal to 0. So that it's already nice and separate. You don't have to do anything other than integrating this step and getting a solution for something like y of x equal to integral plus a constant. Something like this. Section 1.4 talks about what are exact ODEs and then what are integrating factors. Okay. So if you have a function, for example, you have u, okay, you consider the differential of u. Suppose, okay, let me back up 1 second. Suppose u is a function of two variables x and y, two spatial variables x and y. Okay, what would you think about, or how would you write du, the differential of u? This is a formula from calculus which some people just remember or memorize. There is another way to remember this formula, which I can tell you if you are not, if you tell me that you don't know how to write du, or if you're not sure how to write du. Louder, please.
X, D, Y, X.
You mean partial?
Yeah.
Say that.
X, like partial differentiation of the function X dx dx plus
Plus partial with respect to y
y dy.
dy. All right, thank you. Can any of you give a interpretation of this? Why is the sum of these two equal to this? What is this? What is this? What is this? What is this? Yeah.
Partial differentiation, like when I am partially differentiating the function q with respect to x, we are keeping y, assuming y as a constant,
Okay.
and like here x is a constant.
Okay. So how does that answer my question? How does that give you an interpretation of this expression? You are basically completing what you are saying. It's not the answer to my question. My question is, how do you interpret this, or how do you explain this statement?
We have a physical thing on U, and we want to see the variations of U in a minorly different spatial.
That's what is differential. Okay.
And then we move in a component of X.
I'm going to pause you there. What you're about to say is probably correct, but is completely unphysical. Can you give a visual, physical way of explaining that?
So imagine we have a distribution of temperature here in this room.
Okay.
And we want to see, all right, so we have a temperature of a point here, and we want to see how it varies in a very small step.
So if you have a point,
Yeah.
and if this is x direction and this is y direction, what does this represent? It represents that how the rate at which your quantity is changing along x direction, along a line x direction. And this represents the change along another direction. You can call it y or whatever you want. Okay. Just look at this term here and tell me what it means. You are taking the rate of change with respect to the direction multiplied by the distance traveled in that direction. That gives you the contribution, or that gives you the component of change in y along x direction. And you can say the same about the y. This is just taking the change or rate of change along the y multiplying by the rate at the change in y itself. You add these two, you get the total change in u. If you are just saying, okay, x is changing, y is changing, what is the total rate of change of y? I'll try to give you another example. Suppose you are thinking about the cost of milk, let's say a commodity like milk. You know that your milk price went up by $2. And let's say two factors contribute to the change in price, which is the cost of producing the milk and cost of transporting the milk. If you are saying the cost of producing a gallon of milk is X dollars, and then you know how much milk you are buying. You might buy like 10 gallons or 20 gallons, whatever. And then the cost of transporting the milk per mile is so many cents or so many dollars. And you know how far your milk has to travel. Maybe it has to travel from Wisconsin to here for you to actually use it. So you know how much distance it traveled. So this is like saying, if I write it out in words, it might make more sense. You can almost try writing. You don't have to wait for me. So if I write U is the price of milk. Okay. X is production cost. Production cost. So I'll write du over dx is like saying dollar per gallon. And okay, I shouldn't say X is production cost. I'll say X is gallons of milk. How many gallons that you actually consume? So du over dx multiplied by, I'm sorry, partial u over partial x multiplied by dx is like saying dollar per gallon multiplied by gallons consumed. This is how much milk you are. This is the actual commodity cost. It is the amount of milk or the price you pay for the milk. And then let's say du over dy is the dollar per mile transportation cost. So if you write y is the miles transported. So I have du over dy multiplied by dy equal to dollars per mile multiplied by miles transported. Ultimately, you care about the price of milk. So if you want to know what is the total change or total cost, change of cost, that will be du equal to, I'll write it in words, cost of commodity plus transportation cost. This is sort of a detour, I agree. But whenever you use this either in its differential form or in difference form, you got to understand that you are looking at the total change in some quantity, which is affected by more than one quantity. Yeah. This one? All I meant to say was if you integrate this, you get a solution for y after some rearrangement. Okay. So if you answer the next question, you pretty much have figured out the exact ODE's concept. Okay. If you have a differential equation that is written as m dx plus n dy equal to 0. Suppose you have a differential equation written in this form. How do we find out if this is an exact ODE? What is exact ODE? An exact ODE is one of the form du equal to 0 or partial u over partial x dx plus partial u over partial y dy equal to 0. Any given equation in this form, how do you know if it is exact? I know it's the summer. You just got a little rusty. Come on. How do you say if this form and this form are equivalent? That's the question.
Integral of m with respect to x has to be equal to the integral of n with respect to y.
You're sure or you're guessing? If these two equations are equivalent, okay, that is, if you can write m equal to du over dx and n equal to du over dy, how do you know if this is an exact differential? How do you know if this is something you could just write as you can just integrate term by term, that m, even if it contains y terms, is still an exact differential? I know you have the answer. Tell me.
U is like, U is a function, so here, like if we integrate with, like for m, if we integrate with respect to x, we get u, and here, if we integrate n with respect to y, we get u. These two should be equal.
Well, if we are able to integrate, why bother do all this? Because integration, if you can do directly, you don't have to take so much care to check whether it's exact or not exact. You have a function, u. It depends on two variables. Think what property of its derivatives can be used to get out of this situation. So if you take partial derivative with respect to x, the implication is y is constant. When implication is x is constant. You can consider the partial with respect to y of the first derivative and the partial with respect to x of the first derivative. And you know from your calculus that these two must be equal to each other. The sequence in which you do the differentiation does not matter, as you would have learned in your calculus. I'm saying that as though it's a fact of nature, but how do you actually reconcile with it? Why is it true? Why is this equal to this? It's making these kind of interpretations is what is going to appear on your exams. You'll be given a long-winded problem statement which you have to read and translate into math. So I'm giving you math and asking you to translate it into words. Why is this true? Okay, you are going to find out and tell me on Wednesday. Think about it. It's not asking you to solve something new, just some fact that you have learned since high school. I'm asking you to tell me why is it true. Okay. Assuming this is true, if I know that my m is first derivative with respect to x and n is first derivative with respect to y, I can easily say the first derivative of m with respect to y should be equal to the first derivative of n with respect to x, right? If this is true, that is, we say, if this is true, it implies that you can write m dx plus n dy equal to 0 is exact. And if this is exact, it implies this. Let's do an example. It'll just make a little more sense. You try to solve a problem. 2xy dx plus x squared dy x squared dy equal to 0. Now, you can look at this, and as you practice more, you can look at this and just write them in an exact form by just inspection. Like if you keep doing this, at least initially, let's say you call it m, call this n. What is partial m over partial y? That will be 2x. What is partial n over partial x? That will also be 2x. These two are equal, which implies the ODE is exact. ODE is exact. So what if it is exact? If it is exact, you can write the solution u of x comma y is either m dx plus an arbitrary function in y, or it is the integral of n dy plus an arbitrary function in x. Either of them are equivalent. So if you do the first, what are you going to get? What is m dx? Integral m dx. Integral 2xy dx plus k of y. What is integral 2xy dx, which means integration is being done with respect to x? How will you evaluate this? As far as this integral is concerned, y is like a constant, right? So you can just write this is y times integral 2x dx plus k of y, or this is y x squared plus k of y. Okay. You can also take the other option and write u of x comma y is integral n dy, which is x squared dy plus L of x. In this integration, x squared is a constant. So this is x squared y plus L of x. You're getting the same thing, differing only by a arbitrary function in x or y. Are you with me so far? How do you get rid of, or how do you figure out what L or K are? With the provided information, how do we get L or K? Say something, it's okay. I'm not scoring you, or I'm not. I want you to talk, please.
Okay,
Yeah.
let's setting up some boundary conditions.
This is already like an arbitrary function. You are used to seeing arbitrary constant. This is like saying any function that involves x will satisfy this solution. Same thing for this. Yes, somebody else had something? Somebody said something. Who said? Then say it. You have a spokesperson in the class.
I'm sorry. I will explain from class.
Sorry, say that. Yeah. What were you saying?
Like if you set some boundary conditions.
We are not given that. So how do you evaluate it now?
Yeah, finding some relations between X and Y.
This is the relation. The way you answer that question is you can't. With the provided information, this is it. You can't go further until more information comes. So if I tell you the value of u at x equal to a and y equal to b is such and such, with that maybe we can narrow down. Or if we say u at x equal to 0 and y is some known function, say k of y, then we can further narrow it down. But if this is what the problem is given, this is where how far we could go. So part of using math as an engineer is figuring out how much the information you have can take you, how far can it take you. You shouldn't be delusional in thinking that with just this information, you could write more relations. You can't. You should be able to say, I can't. Okay. So there will be such trick questions in the exam. Be forewarned. Okay. All right. Let's do one more example. Okay. Problem 9 from problem set 1.4. Problem 9 from problem set 1.4. E power 2x times 2 cos y dx minus sin y dy equal to 0, and y of 0 is given to be 0. This is provided.
The previous question, we know that the both answers are equal. So why can't we say that Lx is equal to ky and they only have to be a constant?
You can do that. I think you could say since this function matches, yeah, I guess that is fair. You can say you can combine them to write u of x comma y equal to x squared y plus a constant. We'll go that far. Good observation. Okay, so how do we solve this? This is the ODE and this is the boundary condition given. We are solving for y. Okay. Solve for y of x. You have e power 2x multiplied by something equal to 0. What do you do next? E power 2x, if you are x, you assume that x is a real number, which is anything between infinity but not actually infinity. This is finite. Okay, e power 2x will always remain finite if x is a real number not equal to infinity. So you could just say e power 2x cannot be 0. So the other term has to be, so 2 cos y dx minus sin y dy equal to 0. You can do this using the m and n. Try to first prove to yourself that this is exact, which you will find out it is. You can also do cos y multiplied by dx or wait, is it 2? Oh, wait. So this is I don't want to skip a step because I lost my step there. So if I write partial m over partial y, that is minus 2 sine y. Partial n over partial x gets you 0. Okay, so that is not exact to begin with. Now we have to see how to make it exact. Well, wait, I made one more mistake here. Yes, it is true that e power 2x is 0, but if you actually keep it along with it, it will help you explain the 2. Then it will be exact. So let's back up one step. This is also something you should look for. I will make this. Okay. You should be able to catch this. All right. So if I have 2e to the 2x cos y dx minus e to the 2x sin y dy equal to 0. So I can write this as cos y multiplied by differential of e power 2x plus e power 2x multiplied by differential of cos y. I'm doing this so that by inspection also you could solve most of these problems. To do it through the mdx and ndy, some of it you can just directly integrate them. Look at this. This is differential of e power 2x times cos y. Won't you say that? Right? And now if you integrate both sides, you're going to get e power 2x times cos y equal to an arbitrary constant, because the integral of 0 is a constant. You use this provided boundary condition, you're going to get that e power 0 is 1 times cos 0 is 1, c is equal to 1. So y of 0 equal to 0 implies c is equal to 1. So this would be the general solution. Okay, and e power 2x cos y equal to 1 would be the particular solution. Quick question. How many arbitrary constants or functions will be in your general solution? For this equation, there is one arbitrary constant. How would you estimate, or how do you come up with the number of arbitrary constants that would be in your solution?
Isn't always one.
It isn't always one if your differential equation is in first order.
Most, I know that like you have multiple, yes, you'll have like C1, C2, but at the end, if they're all just arbitrary constants, couldn't you combine them into one?
No, not necessarily. So not always that they'll appear as products or sums. Sometimes you'll have C1 multiplied by a function plus C2 multiplied by a function, which can't be combined into one constant. So my simple question is, how many constants will appear for a given or ordinary differential equation? Exactly. So if you have a first order differential equation, you can almost count the order and that should be equal to the number of constants. Second order, 2 constants, third order, 3 constants and so on. So I want you to remember that it's a very self evident fact that if you integrate n times, you will be left with n constants. And you need n pieces of information or n boundary conditions to eliminate all those constants. Okay. That will come useful when we go to the second chapter on second order differential equation. Okay. So in this section 1.4, we saw exact ODEs. There is also a discussion about integrating factors and how to find integrating factors. Okay, which I ask you to self-study. Okay. So the next topic we are interested in is in a particular type of exact ODE called Bernoulli equation. You may ask what is special about it. It is a good model for anything that decays over time. Anything that has an exponential decay is typically represented using Bernoulli equation. And whatever we study under how to find integration factors is like a general procedure for any differential equation. We are going to see a particular application, or we are going to take a particular formula and just learn about that formula, do examples around that. And the idea is, if you know that a concept called integrating factors exists, when you need it, you know where to look for it. I can't possibly teach all possible ways or techniques. I try to pick and choose things that I think are useful for you and mention some names along the way so that years later you would think, oh, that rings a bell. I might just go look up this book to find out this method. You don't have to learn everything in one course. That's my point. Okay. So the Bernoulli equation So the Bernoulli equation is of this form. Don't confuse this with the Bernoulli equation that may appear in fluid mechanics. Bernoulli did a lot of good work. His name appears in many places, so this is different. Okay. Y dashed of x plus P of x equal to R of x. I believe that's the form. P of x times y equal to R of x. This is the general form of the Bernoulli equation. Okay. So if you consider just the left side equal to 0, y dashed of x plus p of x times y equal to 0, this equation is called a homogeneous ODE, or sometimes the homogeneous part of the ODE. You take this homogeneous part, you can write this as dy by dx plus p times y equal to 0, or you can write dy by y plus p dx equal to 0. Simple enough, no magic so far. And you can integrate this to write natural log of y plus integral p dx equal to 0. Or I should say integral p dx equal to a constant which I call alpha. No, alpha is usually used for something else. I call it C1. So I can write this as y of x equal to uh, exponent of negative integral p dx plus constant C1. Can I? Just turning the logarithm into a exponent from this step to this. Okay. So I'm going to write this as exponent of minus integral p dx multiplied by exponent of C1, and exponent of C1 I'll start calling it C. Okay, it's just a constant, right? So this is y of x equal to C e power minus integral p dx. This is the solution, of the homogeneous form. So for the non-homogeneous form, I don't know why they call it non-homogeneous. Maybe it should be inhomogeneous, but I guess it's not about uniformity. It's about not being equal to 0. So that's why non. For the non-homogeneous form, I'm just going to skipping steps that are explained in section 1.4. I'm skipping steps that if when you self-study section 1.4, you will be able to fill the gap. Okay, so I'm skipping those to write y of x equal to, that is the final step, e power minus h integral e power h r of x dx plus c plus a constant c, where h equal to integral p dx. So this is the solution to the Bernoulli equation. We're just like essentially parachuting this result in so that you could solve problems of this type. Okay, just one example of a simple first order ODE that has physical relevance. What is that relevance? Bernoulli equation of the form y dot plus p of t times y equal to r of t, where t is a time variable. Most commonly is found in electrical circuit and in general unsteady transient dynamic or transient dynamic problems. Okay. So one example is given in the book, example 2. So section 1.5, example 2. It's an electrical circuit problem. Okay. So you have a resistor and an inductor connected to a source. I know many of us are not electrical engineers, neither am I, but what essentially it boils down to is a differential equation that describes the current through the circuit di over dt plus r over L times I equal to E of t over L. This is E of t. If you ask the electrical engineers, they'll tell you how they can apply Kirchhoff's current rule to arrive at this formula. Okay. Usually in exams, especially in this course, if you're going to get anything outside mechanical engineering, anything that doesn't involve force balance, I will provide you this equation. If it's a spring block system and you are expected to write force equal to mass times acceleration, you're on your own. But if it's electrical circuit or anything that's got to do with rate calculations, which is not typically taught in engineering, in the sense it's not, it's if either it's simple logic or Newton's law, I expect you to know. But if it's something specialized like electrical circuits, I'll provide you the equation. Okay. So this is your equation. I is nothing but your y. P of t is just r over L. E of t is a time dependent function given to you, which is r of t. You are asked to solve for the current as a function of time. This is the solution process. And for that, the initial condition is provided. I of 0 is 0. Of course, the R values and L values also provided. R is 11 ohms and inductance is 0.1 H. Interestingly, I don't know what is H. Maybe electrical engineers do know. But I want you to focus more on this and be able to solve it using the formula that we have written here. So if you go through the steps, first of all, what is H? If it helps you, I would definitely encourage you to write the equation in the standard form. Okay, I would write this right next to what we know. So H is integral P dx. In this case, it is integral R over L dt. Okay, R over L dt. So you're going to get R over L times T. That is H. That is H. Okay. And then you want to write this integral. Integral of e power h r of x dx, which is integral e power r over L times t multiplied by r of x, which is whatever that appears here, e of t over L dt. What is EFT? Before we look at the book and just get a mathematical formula for EFT, what is EFT? Just not deep electrical engineering, but at least tell me what you understand about a voltage source.
That the voltage passing through it over a given time.
It could be as simple as a battery. Okay, you just put a battery, it supplies a constant voltage. It could be a capacitor which has a fixed amount of charge and E of t just decays over time. Or it could be a switch which went from 0 to 1. So for some time you had 0 and then you went to 1. So you can represent any of those. The point here is whatever your voltage source is, it can be represented using a mathematical formula. You figure out that formula or it is given to you in the problem. You throw this into this integral, complete the integration either analytically or if necessary numerically, and you get a formula for this integral as a function of time t, and that again fits back into here. This is your general solution. Okay, so what we are seeing under section 1.5 is essentially a formula for Bernoulli equation, which just happens to be a very commonly occurring ODE relevant to transient problems. Okay, something that you are given as a sample or as an example of ODEs. The more general ideas are in section 1.4 under integrating factors. And even before that, we saw variable separation, which is like saying exact ODEs can be separated and integrated. So these three topics together gives you a sense of what are first order ODEs and how they connect or how they might be solved when you encounter them in your analysis. Okay. I could definitely do more examples, which I hope to do. But what I would suggest is section 1.3, 1.4, and 1.5, go to the respective problem sets and start attempting those problems. Okay, and you have to make it a habit to try those. And if you do want help, you should ask, because I don't keep a fixed office hour. I'm hoping you would tell me when you want to meet me. Okay, so you have to ask. If you sit back and just wait, nothing will happen. Okay. Lastly, I do plan to record these lectures, but I don't intend to make it a habit of sharing, mainly because if I start doing that, the attendance drops precipitously. I've seen that happen many semesters. People stop coming to class. So I want you to come to class, but at least a few days before the exam, I will post it on YouTube and share the link with you, okay, so that you can use it to study if at all it helps you. Okay. Any questions? Yes. H is just like a symbol used to denote PDX. It's not a real integration operator. It's not a solution to anything. It's just this formula evaluated and we call it H. That's all.
The numbers when you put the homework suggestions, those are from the 10th edition.
Yeah. I have not used any other edition, so it's 10 mostly.
Library, like the highest I got is 7th edition.
Oh, a library is so out of date.
Do we need to buy the 10th one?
I don't insist on buying. If you could rent it or if you could borrow from somebody for a semester, I'm okay with it. Somehow the numbers, I have only the 10th edition. So you try to find the 10th edition, you don't have to buy it. Okay, you can borrow, you can ask.
The open book exam.
Let me think about it and give you all a definitive answer by next lecture, whether it's going to be an open book exam. I am leaning towards closed book exam, but I don't know. Students always seem to think open book is to their advantage. Sometimes it's not. Maybe we'll come to that compromise. You can bring like 1 or 2 sheets of paper, whatever you can pack in 2 letter-sized pages.
Be giving us that ability to change it.
No, I don't think I'll ask anything different because you have access to the formulas. I'm looking to see if you can distill a engineering analysis problem into a math equation. I don't lift one problem that's already in the book, so that having the book will not be an advantage in that, but maybe it will save you the effort of preparing those 2 sheets if you had an open book exam. So as far as I'm concerned, I'm okay with, yeah, 2 sheets of paper. In fact, that's very generous because it's only 2 modules. You're getting 2 sheets of paper, not one. Okay, so to wrap up, just a couple of days before the exam, or maybe some 3 days before the exam, I'll try to post the YouTube recording. Okay. All right. Thank you.